Okay, let's continue on in terms of our kind of big picture in terms of the technology that's used in decentralized finance. So we've actually already talked about incentives, and we will further talk about incentives in terms of how this ecosystem actually works. So incentives are really key. So every single step here, so the miners are incentive to do the work that's necessary for the security and the validation of transactions. We've got the keepers that are incented. We've got the possibility of different protocols incentivizing people to interact with the protocol. So we've got many different levels of incentives, and this is a key thing. It is kind of interesting that just within the network, within the Bitcoin and Ethereum network, there's no direct reward for running a node. So if you're not mining, there's no reward for that. And you can maybe understand a company having a node or a university, but I guess the point I'm making is that while incentives are an important part of this ecosystem, there are still some gaps. Latency, I've talked about already, and it's a big issue. And I spent a lot of time in the fourth course talking about different technologies that can address the main issue. So Visa routinely can do 24,000 transactions per second, and their capacity is up to 75,000 transactions per second. And if you look at Bitcoin and Ethereum, it is trivial compared to that. So that's the reason that Bitcoin cannot be a credible transaction mechanism on a large scale, given the current implementation. Ethereum looks like it falls into the same category, but the next version of Ethereum that will be implemented likely in early 2022 will have capacity that will rival Visa. In my opinion, that's still not enough, so additional work needs to be done, but still, it's a big jump going from 18 to 75,000. Data. So blockchain contains data. So blockchain is like a database. Think of it as a database, but it's a very special database because it is immutable, so you can only add to it. And it's also redundant in that the same database resides on many different nodes. So the question is, well, what about putting data into a blockchain? So there's many different things that we talk about. It could be a transaction where I'm going to move, I move some token from one person to another. It could be a smart contract I put in. But I think I've told you already that this is very general technology. So we could put things that are relevant for a supply chain in a blockchain. But that takes space. And remember that every node on the Ethereum blockchain has got that entire history. So in the future, of course, the price of data continues to decrease at an exponential rate. So if you look historically at how much it cost for a gigabyte of data, it's really striking that the price has plummeted. So today it's about 1 cent. So in the future, I think blockchains will be able to have more data. But right now, the data is quite limited in terms of what we can do. But that doesn't mean that we can't have a technology that allows for more data to go into a blockchain. Computing power, you've probably seen this graph before. It's maybe a little different than the usual one you've seen because I actually measure calculations per $1 in constant dollars. And notice the y-axis is double exponential. So there's a limit to Moore's law in terms of the actual depth of a chip. You go to the atomic level, there's going to be some quantum effects. So there's a limit to Moore's law, but there's also another computing revolution going on in terms of quantum computing. So just to be clear here, the quantum computing is irrelevant for cryptographic hashing, but it is relevant, as I mentioned, for the digital signature algorithms. And I'll have a little more to talk about that later. Let me give you an application to kind of end this subsection. And this is from an assignment in my course. So at Duke University, all the students deploy multiple smart contracts. But the first one that they deploy, they basically send a hash to that contract. So a SHA-256. And they send it to that contract. And that's the mechanical part of the assignment. And the deeper part of the assignment is, how could that be useful? So sending a hash doesn't really take that much space. It's 256 bits. So it's fairly cheap to do. So why would you want to send a hash to a contract? Okay, so this is what they think about. And it's really interesting, all of the possible answers that come out of that. So for example, let's say you've got an idea and you want to be able to prove that you had the idea at a certain point in time. Maybe it's an idea for a new business and is contained in a pitch deck. So you take that pitch deck and you do a SHA-256 of that deck. And then you deploy that to a smart contract. And when you do that, we know exactly the time that that hash was put into the smart contract. And the hash is there for anybody to see. So then suppose that a competitor comes up with the same idea. And you say, well, no, I had this idea first. And then you send the deck to them, and the date on the deck is, let's say, 6 months ago. And the competitor says, well, I don't believe this, because it's really easy to change the date on a file. And then you tell the competitor, so no, do a cryptographic hash of this file. And then go check this particular block on the Ethereum blockchain. And you can see that this document existed as it exists exactly today, 6 months ago. And the exact time is there. So this is basically a proof that this existed at a particular point in time. So this is, so many different ideas. For example, suppose you have a contract and you've got electronic versions of the contract. And there's a dispute. And in the dispute, there is a disagreement because the two electronic versions are different. And you have to go to court and fight it out. So now think of a different world where the two parties are trying to put together a contract. They agree upon a contract. You take a cryptographic hash of that contract. You deploy that hash, you send that hash to the Ethereum blockchain. And then in the future, if there's any dispute over the version, so party A says, oh, it's my version, it's the true version. And party B says, no, my version is the true version. It's really simple. You take a hash of version A. Does version A's hash match what's deployed to the Ethereum blockchain? Yes or no? And let's say it's no. And then you go to B's. You do the hash, you check the Ethereum blockchain, it matches. Therefore, A's contract's been tampered with, and the B's contract is the true contract. It's a great idea. So there's another assignment I'll talk about, and it's a lot of fun also. So this is a slightly more elaborate smart contract. So I tell the students to send a hash to it. And then the contract has got the ability to reassign that hash to another address. So I get them to send the hash to somebody else, the teaching assistant in the course. So that means that when that's done, the teaching assistant has ownership of that hash. And then, of course, that's the mechanical part. The other part is, how is this useful? And it is very powerful, smart contract. Indeed, I tell my students that this is the single most valuable assignment you will have at Duke University because you can reuse it. This contract allows basically the exchange of anything that can be digitized. Okay, so that hash could represent your ownership of something. And then you can reassign the ownership to somebody else. Okay, so very, very powerful idea. It's kind of similar to an NFT. It's not as elegant, and NFT's got much more functionality, but it's the same idea. So you've got something that you own and that's proven in that smart contract. And then you're able to reassign, to sign over, using that digital signature, sign over the ownership to somebody else. And then they are the owner. If they want to transfer it, then they need to sign it over using their digital signature algorithm in the same way. So very, very cool idea. So lots of applications here.